Okay, so for this section on differentiation application, it is an application. Okay, we are exploring something called stationary point. So it is called an application because we'll be making use of dy dx. And in addition, in this application, we'll be using something called second derivative. Okay, so I need to introduce you the notation and also what how how are we going to get the second derivative. So first of all, usually dy dx is known as the first derivative. So in a way, that is the first time you differentiate. So usually when you get y and then you do a dy dx, that's where you get your dy, that's where you get your first derivative. Okay. And then here is the second derivative. So if you look at the notation, it looks a little bit different. It's like d square y over dx squared. Okay, so please write it properly. So your second derivative is dependent on your first derivative because we're going to differentiate it one more time. Okay, so I also need to show you another type of notation. Sometimes you will encounter fx. So sometimes you will encounter fx. So dy dx, right, is equivalent to f prime. So you might see this kind of notation in O level. Second derivative will be f prime prime. So in case you see this kind of notation, maybe you don't see this much in differentiation, but you might see this in integration. So this one will still be called the first derivative, and this is still the second derivative. Okay, and how you obtain it is the same thing. You differentiate dy dx one more time. Okay, so to make things clearer, okay, I show you a generic example first. So this is a very simple y equation. By now, all of you should be able to differentiate. Your bring down power minus power should be in your head already. So from here, you should be able to tell me that you are getting this as your first derivative. So before you go on to the second derivative, do check that your dy dx have no issue. So you do bring down power minus power one more time. So that is called the first derivative and the second derivative. There must be a use for the first derivative and the second derivative. So we'll be using it to apply to the idea of a stationary point. Okay, so this is the basic notation first. Of course, it's not so easy to get second derivative if let's say your first derivative is already difficult. So sometimes even your first derivative, you might need a product rule or a quotient rule. So if your first derivative is already difficult, sometimes the second derivative is even worse. Okay, so what will be the use of the first derivative and second derivative? So I'm going to jump to example 2 to show you we are going to use the first derivative to find something called the stationary point. So there'll be this thing called stationary point. There's another name for it that's called turning point. And we use the definition of dy dx equal to 0. So if you would like to calculate stationary point, the definition is dy dx equal to 0. It is like your increasing function. So far, you already learned increasing function. Increasing function means the dy dx is always positive. Decreasing function is dy dx always negative. So that is the definition of an increasing and decreasing function. So in this case, the definition of a stationary point is dy dx equal to 0. Okay, you can either memorize this definition or if you would like an understanding. So why do they decide that dy dx equal to 0 for stationary point? Because stationary point can either be a maximum point. So this is the turning point. The turning point can be the highest point and the lowest point. And every turning point, if you try to draw a tangent, it is actually horizontal. So if you try to draw a tangent on the highest point or the lowest point, it will actually end up horizontal. So this is a gradient. That means the gradient is 0. So if your tangent is horizontal, that means the gradient is 0. And don't forget, when you were learning tangent and normal, you realize that dy dx represent gradient. So that's why it all boils down to dy dx equal to 0 if you would like to be finding the coordinates of the stationary point. So I'm going to be using a very generic example to show you the calculation of the coordinates. So it's actually quite an easy thing during O level, provided you don't make careless mistake. So if you look at the equation of the curve, you perform your dy dx. So this is quite easy. Okay, so if you would like stationary point, okay, go for the definition. The definition will be dy dx is equal to 0. You set your dy dx to 0, it becomes something like a normal algebra. So this is a quadratic. So it's like first bracket equal to 0, second bracket equal to 0. Okay, so if you look at the instruction, if you set dy dx to 0, you will be able to obtain the x coordinate of the stationary point. But you have not gotten the y coordinate yet. So in order to get the y coordinate, you should be putting in the x into the equation of the curve. So you put your x back to the equation of the curve. So you just sub it in. It will get you y equal to 4. Okay, this part will get you a 0. So all in all, at the end of the calculation, you will be able to obtain that 0, 4 is a stationary point. 2, 0 is also a stationary point. Okay, all we know that is they are stationary point. We wouldn't know whether are they a small point or are they a set point. So at this moment, you only know that these are the coordinate of the stationary point, or you can call these are the coordinate of the turning point. Okay, so that will be one of the use of dy dx. So we use dy dx equal to 0 to find the coordinates of the stationary point.